Similar to section 7.5, we've got a summary and strategy section for dealing with arbitrary series that we might encounter. And this is section 11.7, which is summary and strategy for series. So we have several tests. I think we've got 7, maybe more, depending on what you consider to be a test. And given a single series, it's probably not a good idea to just try tests until you get something with the result, because you might waste a bunch of time dealing with a test that you may not, or limit that you may not be able to evaluate. So first up, we have immediately recognizable types of series. These are p-series. Well, we might have p-series, which is the sum 1 over n to the p, which is convergent if p is greater than 1, and divergent if p is less than or equal to 1. And series properties might help a little bit in identifying these, because if I have some constants inside the series that I can factor out, I might consider trying that before starting to do tests. And there's geometric series, which looks like a times r to the n, where a is some constant. Well, actually, a and r are both constants. In which case, r is the common ratio, and a is just maybe some extra stuff that's been tacked on. And this converges if r is less than 1, is convergent, and if r is greater than or equal to 1, then it's divergent. But if it's convergent, then I actually know that this is going to be equal to the first term over 1 minus r. But you might be able to immediately recognize some other types of series, such as telescoping. I will have a series in which the terms are eventually self-canceling. So we've seen a simple example of a telescoping series, but I also have a more complicated telescoping series where I have, let's see, I might have 1 over n minus 2 over n plus 1 plus 1 over n plus 2. This would also be an example of a telescoping series, but it's a little bit more complicated. It takes extra time for us to properly cancel everything out. If I start at n equals 1 to infinity, then my partial sums, we'll look at s sub 4 for example, is equal to 1 minus 2 over 2 plus 1 over 3. Let me rewrite this one as 1 over 1 plus 1 over 2 minus 2 over 3 plus 1 over 4 plus 1 over 3 minus 2 over 4 plus 1 over 5 plus 1 over 4 minus 2 over 5 plus 1 over 6. And it's tempting to say things cancel in here, but why don't we look at this more carefully? Let's look at this 2/3 minus 2/3 here, for example. This cancels with the 1/3 at the end of the first term and the 1/3 at the beginning of the third term. Similarly, this minus 2/4 cancels with the end of the second term and with the beginning of the fourth term. So this is a telescoping series which has a more complicated cancellation, but we'll see here, if I added on the fifth term here, then this and the beginning of the fifth term would cancel as well. So for less immediate series, if n factorial, or actually if a factor of the series of the terms is a factorial, for example, n plus 2 factorial over 3 to the n, or n to the n squared over n to the n, times n factorial, or other similar such things, then I'm going to want to use the ratio test. If a major part of my terms has a power of n, then I'm going to use either the root or the ratio test. And by that I mean I have something to the n somewhere. We're going to use either the root or the ratio tests. They are often interchangeable in these situations, but sometimes the ratio test is going to be more work than the root test. Maybe the root test will be more work than the ratio test. There's not really a way to tell until you actually get into doing it. If you have something to the end and you start with the ratio test and you get tired of the work, maybe look at the root test. If you start with the root test and you get stuck with the limit, maybe try the ratio test instead and just power through it. If there is a -1 to the n in some form, then we're probably going to use the alternating series test. But what we need for the alternating series test is we need to be able to separate the alternating part, and everything else needs to remain positive. So sometimes the alternating part can be somewhat hidden. For example, I could have cosine of n pi, or I could have tangent of, see, when is tangent equal to 1? That's at pi over 4. I skip 3 pi over 4, and I go to, actually no, 3 pi over 4, that's -1. And then when I get to 5 pi over 4, that's +1 again. And then at 7 pi over 4, it's -1 again. So it looks like odd multiples of pi over 4 odd multiples of pi over 2 for sine, and maybe some others I won't really know until I look at it and try to evaluate it. Another test, if the alternating test doesn't fit, so maybe I have, if I separate off the alternating part, maybe I still have some occasional negativity in the remaining part of the problem, I might consider absolute convergence. And I might be able to brute force that, or depending on my problem, this could mean using the root or the ratio test again. If your problem looks like it would make a good integral problem, that means when I look at it, it looks like, hey, if that was an integral, I could do u substitution. That's a good indicator. Then I'm going to want to try to do the integral test. But I need to make sure that I satisfy the conditions of the integral test. And so we'll recall that the integral test needs positive terms. Eventually is okay. We need decreasing. And we can show that by either checking a sub n plus 1 greater than or less than a sub n, or we could translate a sub n into a function of x, since we're already doing that anyway, to try to do the integral test, and look at f prime of x. If f prime of x is less than 0, then we're going to be a decreasing sequence. And we need continuous, which basically means I don't divide by 0 anywhere from whatever to infinity. If my series looks algebraic, then I'm going to want to compare or limit compare to a p-series. And in general, if the series has a couple of extra constants, maybe the random thing is squared, maybe they tossed in cosine of n or sine of n, and they added, 17 squared or something. But if I removed all of those, then it would look like one of the immediate series, like it would be similar to a p-series, or maybe it's almost a geometric series, but I have a bunch of extra crap added or subtracted or divided to it. That makes it not a geometric series. Then we're going to try to do a limit compare or a direct comparison. But also, if none of the other tests work, you're going to try comparing or limit comparing. And finally, or perhaps first, test for divergence. The limit of the terms, given a series, the limit as n goes to infinity of a sub n equal to 0 is required for convergence. But it is not enough for convergence. That example being, of course, the sum of 1 over n. But the limit as n goes to infinity of a sub n being not 0, or even being infinity in the worst cases, is guaranteed to diverge. The test for divergence is often one of the first things you want to check when approaching a new series, but maybe eventually you get used to it enough that you kind of put this one off to later. I should reiterate, though, that up here, when I have the root or the ratio tests, remember that the root or the ratio tests will not work on anything related to a p-series. If your series limit compares to a p-series, the root and ratio test will not work. So if you do the root and the ratio test and you get inconclusive, that's actually a good sign that your series may be similar enough to some p-series that you can limit compare to an appropriate p-series and be able to determine the divergence pretty quickly. So if I'm not sure what kind of a p-series to compare to, actually this doesn't even have to be p-series, but an uncertain comparison series, then let's consider this. If the limit as n goes to infinity of a sub n over b sub n is 0, that means a sub n is significantly smaller than b sub n. Or it says that b sub n is too big. Because if b sub n was a convergent series, this would be fine because a sub n is smaller and therefore also convergent. But if b sub n is divergent, then a sub n is smaller, which could be a smaller divergent series or actually convergent, so we can't tell. So I might want to choose a smaller b sub n. Likewise, if the limit as n goes to infinity of a sub n over b sub n is infinite, that means a sub n is much larger. Or it means that b sub n is too small. So if b sub n was a divergent series, this would be fine because that means a sub n would likewise diverge since it's larger. But if b sub n is convergent, then a sub n could be a much larger convergent series, or it could diverge, I'm not sure. So in that case, I should choose a larger b sub n to compare with. A good example of this, I believe, is number 40 in the limit comparison section. So if I consider looking at some collection of series, if I have the sum of n minus 1 over 3n plus 2, I see here that I have a rational function of polynomials, which is considered algebraic. So I would try to compare this with a p-series. But if I'm thinking about comparing it to a p-series, that means I'm essentially going to be looking at the largest terms in the top and the bottom. But the largest terms in the top and the bottom are both n with the power of 1. And the limit, as n goes to infinity, of n minus 1 over 3n plus 2 is just going to be the coefficients giving me 1 minus 1 over n over 3 minus 2 over n. These go to 0. This gives me 1/3, which is not 0, which is necessary for convergence. So I just accidentally did the test for divergence. On the other hand, if I had something much more complicated, like the square root of n to the 5th plus 1 over 3n to the 4th plus 2n squared plus 1, this also counts as algebraic. I've got a square root here, but that's okay. I would expect to be able to compare this to, let's see, n to the 5 halves divided by 3n to the 4th. But I've got pluses everywhere, and I'm not too confident in my ability to grow or shrink this. I don't know if I remove all those numbers, if I'll have a bigger or a smaller fraction. So I'll just do a limit comparison. And I should expect 4 minus 2.5. This looks like 1 over 3 to the n to the 3 halves, or 3 times n to the 3 halves, which should converge because that number, 3 halves, is greater than 1. Another one from the book, if I had n squared e to the minus n cubed, well, that looks like there's a u substitution. I would try to use the integral test. Or if I had n equals 1 to infinity of negative 1 to the n times n squared over 3n cubed minus 4, well, that clinches it right there. I'm going to use the alternating series test. I just got to make sure that the rest of the stuff is all positive. And again, if I had anything with factorial, I'm going to use a ratio test. But if I had some other stuff that was mixed around, I could use the root or the ratio test for this one because they both have something to the n. Preferably, I would choose the root test for this problem because I don't want to have to multiply out an n plus 1 to the power of n plus 1, or I don't want to do n plus 1 cubed because I would have to multiply all of this out, and that sounds like a lot of work. The best practice we can do for series, though, is just simply doing these problems. So I want to say chapter review exercises, but you probably want to try to avoid anything with an x in it, because the series with an x in the terms, those are called power series, and we can technically talk about them because all the power series need is the root and the ratio test. But as far as doing those problems, tread carefully because they might ask you for some things that we haven't discussed yet, like the terms radius of convergence or interval of convergence. But certainly a good place to start is going to be, well, this section itself. It's going to have an abundance of series for us to play with, but also try to review some of the harder or later problems in this individual sections for each of the tests. Because practice, there's really no place for practice.